All right. I think we are at capacity in this room, so we might as well start. Hi, everyone. Welcome to this session. My name is Hossein. It's my honor to introduce my colleague, Sean Owen, for the talk on building LLMs on your own data. So a little bit about Sean. Sean currently leads, is like the principal practice lead on ML and data science at Databricks. And before that, he was a director of data science at Cloudera. And he has, prior to that, several other industry experience on his background. So he has seen a lot of what has happened in the past, I would say, 20 years in data science and machine learning. Today, Sean is going to talk about how you can build LLMs. This kind of builds on top of the experience we've had with Dolly at Databricks. In fact, Sean gave a webinar on specifically training Dolly about a month ago. So this talk kind of is like the advanced version of that and building on top of that to follow up to that talk. And without further ado, please.
Okay. Thanks, Hossein. Okay, hi, thanks everyone. Yeah, that's me. Indeed, the theme today is using LLMs on your data and maybe doing so without breaking the bank. And indeed, it's a continuation of a webinar you may have seen me in maybe, it's about 2 months ago. So if that was the 100 level version of this talk, the webinar, this is like, it's not the 200 level, it's like the 150 level version of this talk. Safe, okay, yeah. I don't think anything in here is actually forward-looking. Okay, fine. Yeah, right. So you may have seen this webinar. I hope you enjoyed it if you did. And the theme of it was, yeah, how do I maybe use a language model to ask questions about my data, which I think is one of the most interesting, well, it's an interesting use case, but it's also one of the easiest ones. And in that example, we walked through how you might use something like Dolly. Could be other models these days. But I want to build on that because I realized that that was a toy example on purpose. And if you tried to do it, I hope you were successful. But I think you probably had more questions the next day. And I wanted to get into that next level of questions and thinking about how to solve this problem with a large language model. So the use case, as in the webinar, is going to involve blueberries, gardening more generally. You'll see what I mean. And we're going to explore 2 broad things you could do to take a language model and customize it for your data set, again, without fully training a model from scratch for $1 million. And to give you a preview, you have 2 options. You can fine-tune a model or not fine-tune a model. Both are viable. And then I'll close out with some closing thoughts here. OK. Oops. Yeah, blueberries. Yes. So maybe your question, the type of question you're interested in answering is, how do I plant these things? What kind of soil do they like? Let's say you had this question, let's just say. What could you do? Well, you could go to a search engine, ask the question, and search engines aren't bad these days. Here's Google. It gave me a quick snippet. That's actually pretty good information. And it gives me some links. And that's not bad, but to get a deeper answer, a real answer to my question, I'd have to click through some links. And that seems very 2022. I'd really like to have a language model, you like that, synthesize an answer for me. I could even go to a specialist site like Stack Exchange Gardening and ask my question, and I did, and I actually didn't find very good results. OK, there was good information here, but I just wasn't able to retrieve that specialized answer that I really wanted. I can go ask an AI. Here I gave Bard a shot, and Bard did well here. If you want to read it there, that's a pretty comprehensive answer. I've never planted blueberries. This could be completely wrong, but seems plausible. And you might look at that and say, well, yeah, nice, I want that, but can I have it for my data? Because I actually I have a corpus of important information that I want to ask about. So I don't want to just ask what Bard knows. I want to ask about what I know. And although the example here is whimsical, it's gardening, and I'm actually going to use Stack Exchange's data sets, imagine your data here, your private contracts, your private knowledge base, things that Bard and OpenAI definitely haven't seen and you don't want them to see necessarily. So how can I do this on my data? I could go ahead and ask an open language model. And here I'm just loaded Dolly, for example. And it actually does OK, just like these big language models. But I have the same problem. This language model, it's even less likely that it's seen relevant information. And certainly even this open source model has not seen my private information. So same problem, but at least I know maybe I can customize this because it's open source. Okay, yeah, so here's the problem statement. I'm a gardening company. I've got deep proprietary expertise in gardening, and I have a huge knowledge base that I want to answer over. In the reality, this example that you saw in my demo that you can find online is just the gardening Stack Exchange data set. But yeah, imagine your data here. So I want that language capability, but I want it over my data, and I want the flexibility to use and customize that AI, that language model. And maybe that's because I don't want to send my queries to a third party. Tools like OpenAI, they are great. They are state of the art. Sometimes you just can't send that information. You can't send your private information around for regulatory reasons. But sometimes there's a cost reason too. Maybe you just don't need the galaxy brain. You can get away with a smaller language model to solve your problem. So all kinds of reasons you might want to do this yourself. So we're going to explore how you might do this on an open source model. And as I say, if you're interested in doing this, there's kind of two paths here. You can take a model and continue training it with your own questions and answers, or just answers, or whatever, and result in a model that's had that information baked into it in some sense. And that's appealing in some ways. At the end, you have this model that just knows everything. There's no extra moving parts at runtime when you go to use it. And I suppose that's also efficient because I don't have to feed extra information into the model at runtime to give it a clue from my data set. So there's upsides there, but there's actually the other option is to not do that. I don't, so to speak, compile the information into the model, but rather supply relevant information at runtime. So at runtime, I'm going to go find pieces of text from my corpus that look relevant and feed that to the language model with my question. So that's nice in that I don't have to pre-train the data into my model. There's no fine-tuning step. There's no re-fine-tuning necessary if more new information arrives. I just have to be able to look up this chunks of text that are relevant to the question and feed them in at runtime. So there's ups and downs to both paths here, and we're going to look at both. Okay, let's start with fine-tuning, featuring a vector database like Chroma and LangChain here. This is the path you saw in the webinar, if you saw the webinar. Don't worry, I'll recap it. And the idea looks something like this, as I described. We are going to take our data, it's going to be text data, and index it and put it into something like a vector database. The reason we need something like that is because when we get a question, we'll need to go find pieces of text from that corpus that seem related to the question, semantically similar. So we need some semantic similarity search. Frankly, this could be a search engine too, but these days people tend to think of this as a role for a vector database. And excuse me. By the way, hope you saw this morning, Databricks is going to have that piece built in soon. It's called vector search. But at the end, if I do this, then I just have a context plus question that I can feed to any model I want, including an open source model. Here, in that example, which I'll continue here, we did use Dolly, the language model from Databricks. But I want to emphasize that open source moves fast, and I don't even think Dolly is the best choice here anymore. Things like MPT from Mosaic, Falcon maybe. Oh, and by the way, I hope you saw we've intended to acquire Mosaic. Those are maybe even better choices, but the good news is you could plug in anything you want because we're just using the LLM as the language engine, and really any decent instruction following model will do. Oh yeah, by the way, if you want to see a full demo of this, we have a great demo site called dbdemos.ai. They're installable demos. You can pip install a demo and it just sets up everything for you. So this was the example you saw in the webinar. If you want to go look at it, I'm not going to go through it, but hey, by the way, this is a great demo of this pattern, the don't fine-tune pattern. Okay. So yeah, step one, there is some setup though. We got to prepare our text. We've got to get it into some kind of vector index. These are large language models after all, so the text needs to be in a language that the model understands. In most off-the-shelf language models, they're probably going to be trained on a bunch of English text, maybe some other languages. They might have seen some semi-structured language like JSON markdown tables, so they might kind of understand that data, but they're generally understanding text. The data set, however, can really be any old text chunks that you want. It doesn't matter where they come from. It could be from, well, in our case, XML files from Stack Exchange, Word documents, PDFs, HTML, knowledge bases, manuals, wiki dumps, whatever you want. Any sources of chunks of text will do. And although the data set I have in this example is question and answers, it's from Stack Exchange after all, you don't really have to have questions and answers. You just need answers or pieces of information that it can look up and feed into a prompt. That's all you need. If you can get text, you're OK here. We need to index it. 1 second. So the task here is, again, from a question, find relevant text. Relevance in the sense of semantically related. This is, again, a good use case for a vector database. Some use cases involving large language models don't need a vector database. That's not all of them, but this one does. This is a great use case for something like a vector database. Could be a search engine. Really anything that can tell you for this input, this text, this string, show me some relevant other strings. When you use a vector database, you have to choose an embedding function. Often it's fine just to use an off-the-shelf embedding function. I personally go to sentence transformers. It's just a library out there that makes it really easy to access some pre-trained embedding models through Hugging Face. Which vector database? Heard this question a lot. There's a lot of options out here. This example is going to use Chroma, which I think of as the SQLite of vector databases, because you can index things into a database that's just files that you can move around, and you can read those back into memory anywhere you want. You don't necessarily have to set up a service. But there's also Pinecone, there's Milvus, there's Weaviate, there's more, and Databricks vector index, vector search also coming soon. So you have lots of choices here. We needed a large language model in this pattern. OK, let's see. Well, it's going to need to be a text generation model. So again, it's worth observing that we talk about all these language models. They don't all do the same thing. Most of the ones we've been talking about, hearing press about, are text generation models. They're causal language models. They're decoder-only models. They generate more text given a prompt of text. And often we've tuned them to follow instructions. So we start with a question, and we want to continue with an answer. Start with a command, and finish with a response. Not all models are like that, of course. This is not what BERT does, for example. So we need to choose something that does what we want, an instruction-tuned text generation model. Certainly, the big-name proprietary hosted LLM services out there will do the trick. OpenAI, Claude from Anthropic, Cohere. They're very easy to use. No moving parts, just call an API. And they give state-of-the-art performance. So definitely possible to use here. I am going to talk about using an open source model for the reasons I gave earlier, but again, you could plug in anything you want. So let's pick an open source instruction-tuned LLM. Arguably Fluent T5 qualifies here. Dolly does, Mosaic MPT, Falcon. There are more. There's a lot of open source models. In fact, it's almost hard to keep up. But those are the ones I would look at. Probably actually Mosaic MPT and Falcon these days. They have 7 billion parameter instruction-tuned versions, fully open source, very nice. And this, of course, will allow me to use this model privately, run it, and if necessary, customize it. Now, as I say, this is like the 150 level talk. This may be obvious to most people, but in case it wasn't, you're going to need GPUs for this. And this is a different world of hardware concerns. One thing that's not obvious until you get in here is the big limiting factor you will encounter in using GPUs is their memory. That is always the thing that's in short supply when using these things. There's also a lot of GPUs out there. NVIDIA isn't the only maker of GPUs, but let's be real. All the tooling here uses CUDA. CUDA is NVIDIA's library. You're going to be using NVIDIA GPUs when you're using the toolkit, the common open source toolkit here. You can use AMD GPUs too, but we're not going to get into that. In the cloud, you'll find a lot of NVIDIA GPUs. And these are the 4 I think are most relevant today. There's certainly older ones like the K80s. They're just a little too old now. There's certainly ones that are for like graphics processing, like the Pascal series and the M60s. Those aren't quite what you want. It's these 4. There's also newer ones, the H100s and the L4s that are just maybe starting to become available in the cloud. But you're probably going to find these 4. V100, T4, A100, and A10. The V and A100s are training GPUs, although in practice, you can kind of do anything with any of these GPUs. The T4 and A10 are inference-oriented, but you could actually run training on an A10. You could actually do inference on a V100. They're in chronological order here. Their memory size is given here too. And you'll see, so the V100 and T4, they have 16 gigabytes. That's kind of the smallest amount of memory you'll want to mess with these days. There are 32 gig versions of the V100. A100 is the current big mainstream GPU, 40 gigs, going up to 80 gigs of RAM. That's huge, that's plenty. And the A10 as well. And I tried to give some indication of like how hard they are, how expensive or scarce they are combined into one metric. V100's easy to find. They're a bit expensive for their performance because they're a little old. T4s, you can find them all day, no worries. They're not that powerful, but they're widely available. A100's the most commonly available powerful GPU, but they're not that commonly available. If you are on AWS, you'll probably find you have trouble provisioning the P4 types that have the A100s because everybody's provisioning them. So I expect you may end up using the A10s a lot. A10s are also modern Ampere architecture GPUs, 24 gigs of RAM, that's good. Fairly available too, and so you may end up actually training on A10s because frankly, A100s are hard to come by. So those are the ones to know. When you go to pick an LLM, you'll notice they come in different sizes. How big an LLM do you need? Well, I mean, you'll see probably language models, they probably don't make sense below about 100 million parameters. You'll see them as big as 30, 40 billion parameters. And of course, there's bigger ones even past that, but those are probably the biggest you'd ever consider. You'll probably need ones that are at least in the single billion parameters for good enough output. More than 10 billion parameters, I don't know. Those get harder to wield, and they may not be worth the additional language capability. So I might gun for, I think the 7 billion parameter number is a nice sweet spot because 7 times 2, it's 14 gigabytes. That actually fits into 16 gigabytes of GPU RAM in 16-bit. So maybe 7 billion is a good number to start at. You do want to work in 16-bit. The model weights are typically in single precision float, 32 bits per parameter, but memory's at a premium, and 32 bits per parameter is a lot. So you will find that mostly we work in, at most, 16 bits. We load 16-bit versions of these parameters to keep memory consumption down. There's different flavors of 16-bit. There's floating points, there's float 16, and there's bfloat 16, which is just uses the bits differently, more scale, less precision. That's actually probably a good thing. So I'd say you'd always want to work in at most 16-bit, and you can even go down to 8-bit. You can actually have the models work in 8-bit math. This has a price. Well, it has one benefit, half the memory of 16-bit, but it has a price. It's not actually faster unless you're on really new GPUs with accelerated 8-bit math. And because you've lost all that precision in the parameters and the math, the results can kind of fall apart in the network, and you can actually just get no answer. So use it carefully. It's also possible to throw multiple GPUs at a model if you need to load something big and you don't have a huge GPU. And that's where things like bits and bytes and accelerate come into play. If you'll notice this device map equals auto option in transformers that accelerate enables. That lets you actually load a model across GPUs. That's not hard. The only word of caution here I'd give if you're doing that is it will happily load whatever isn't fitting on a GPU onto the CPU, and that's really slow. And so it'll load, it'll look like it's fine, and it'll take like 5 minutes to generate, and you'll wonder what's wrong. So you can also just force it to load on maybe one GPU with, manually. So some things to think about when you're picking and loading your LLM here. Just an example of different results here. I took the 7 billion parameter Dolly model, tried it on a 48 core CPU. You can run these on CPUs. That's just slow. 48 cores running, took about 20 seconds to generate a response. Whereas T4 GPU took 7 seconds in 8-bit. I had to load an 8-bit. Excuse me. And an A10 was even faster. The responses weren't actually that different, I don't think, so it all kind of works. But for speed, you're going to want to use a GPU, and you're going to want to use a new one. So A10's a good choice. Use A10s, maybe a 7 billion parameter model, work in float 16, more specifically bfloat. Okay, so now we're getting to how do we put these things together for the don't fine-tune option. You'll also find, if you start playing with this, that there are a bunch of settings, generation settings, levers you can pull here that you don't really see discussed much in these toy examples. For example, when you use these LLMs through transformers to generate, you can, of course, limit the output size. That's important. The LLMs are going to keep going until they generate the end of in a sentence token, but that might be too long for your purposes. And the longer you let it generate, the longer it's going to take to respond. So that's an important one to know. You can put a cap on the length of the generation. Do sample is an important one too. When do sample is false, then the whole decision about which next word to generate is deterministic. It's greedy. It's always going to pick what seems like the best next word, which sounds good and is because it's deterministic. But in some cases, may lead you to a very kind of boring, predictable results. So you can turn it off. You can turn do sample to true to let it, inject a little bit of randomness in how it picks. And if you do that, then a bunch of other parameters become interesting, like temperature, for example. Temperature is, well, let's just say it controls a little bit how crazy the model, how adventurous the model is when trying to pick the next word. You might turn that up for creative writing, turn it down where you need factual answers. Numbeams is a way to ask it to not just generate one response, but kind of keep the top n responses it's found so far going and explore n ways as it goes. It's going to take n times longer, but you might get a better result because it's got a bunch of candidate responses on the go at any time. And you can also have it return multiple sequences. Nucleus sampling, this is just another way to control, to cut off the long tail of possibilities in the words it might choose to make it a little more conservative. You can penalize repetition. There's a bunch more parameters, and there's a great blog and reference from Hugging Face about a lot of the common parameters. But honestly, I think it's that first page. If these are the ones you're probably going to set, maybe some of these most of the time. That's about all you have to know. Just to give you a sense of how the result might change, I took, again, the default Dolly model and just tried default settings and then changing some key settings to see how it changed things. Now, there's some randomness in these responses, so you might not find the same response if you ran this yourself. But for example, beam search, adding beam search, I think it gives a kind of shorter response there. Turning up the temperature, yeah, that's getting a little more creative. I'm not sure that's a great response for this type of question where I want a concise factual response. Turning down temperature, turning down top P or top K have similar effects, making the generation more conservative and maybe concise. And that's what you see. One kind of troubling thing is I got kind of different answers about pH from different settings. So I'm not sure about that. OK, so that's just a flavor of how these settings might affect. They do affect the quality and the speed of the generation. And you will need to play with this and tune these a little bit for your use case, because you may want longer or shorter, or more creative or less creative responses. There's also another piece here to tune. You remember the part of the setup here is I'm going to go retrieve chunks of text from my vector database and feed that into the prompt. I have choices there. How many chunks of text, for example? Also, how big are they? So I could have chosen, when I was indexing the text, to chop up long documents or into finer and finer pieces. So there's a trade-off there, too. Generally, I think you'd want to chunk into thousands, no, 1,000 tokens, no, characters, sorry, hundreds of tokens, because we're going to pick a couple of these, and we're going to stick them into the context for an LLM. And those language models have a limit to the amount of input they can accept. This is the context window length. And for a model like Dolly, it's actually just 2,048 tokens, which you're going to run through pretty fast. Newer models have bigger context windows, even variable context windows. So this is a problem that I think newer models attack well. But it's something you have to think about. Even if you can fit, again, longer contexts, the model's got to read that before it can start generating. So it will slow down the generation. So it's a choice here. How much data do I want to send in with how many documents? There's also, I think, an interesting question about how to index. In this particular case where I had questions and answers, do I want to find answers that look like my question, or do I want to find questions that look like my question and feed the answers to those into the language model? I actually don't know which one's better in this case. I tried both, which I'll show you, but there are just some design questions here, even in how you index data, that will affect the results. So here's a couple variations. I chose 2 versus 4 chunks of text to feed into the context with my question. And I tried those 2 different strategies. Do I find similar answers, or do I find similar questions and then feed the answers to those? Qualitatively, I got kind of similar results. I don't think in this case it made that much difference. In fact, the top result in every case, most of these questions really latched onto with this formula about 5/8 by 2, 5/8 topsoil, 2/8 peat moss, and so on. So it may not have made a lot of difference here. It might make some difference in another use case. But something to think about when you're designing your Q&A system. OK, let's switch gears. Let's talk about the other option, fine-tuning. And again, the option here was take an LLM and actually tune it on my questions and answers or whatever, and then just use that. So forget the vector database. I just have a model that already knows and the answers to my questions. And that's, although I do extra work to train the model, fine-tune the model, it means I don't have to stick anything into the context at runtime. So that's faster. So I'm going to look again at Dolly, just because, hey, it's the source code I'm most familiar with at the moment. There is a GitHub repo where all the training fine-tuning code for Dolly is. This is code that was used to fine-tune Pythia into Dolly, but you can actually use it the same to fine-tune Dolly into your fine-tuned Dolly as well. It's the same process. And we're going to get to know some tools like DeepSpeed, for example, which you'll find in the training scripts. So yeah, how do you go about this? Well, if you're going to fine-tune, you need to find a model that probably is in roughly the same ballpark as the problem you're solving, that it already does something similar to what you're trying to do. It wouldn't make sense, for example, to take a summarization model and try to induce it to write JSON. It's just not. It was trained to summarize text, not extract JSON or something. Ask, does your task specialize what the model already knows how to do, or does it conflict with it? And if it conflicts, you're probably just wasting your time. Because you're probably going to use an off-the-shelf training script, it's always better than writing your own code. You probably want to understand how that script is taking the data and pushing it into the training process. Do you have similar data? Can you get it into the same form, or do you understand how to change the script to use your input? You also need to think about monitoring. How am I going to decide when to stop training? Because it's actually not that obvious. You will train over your data and train over your data, and you'll see things like loss going down as usual. You can use TensorBoard for that. But you probably have to periodically sample from the model, actually grab a checkpoint and generate, and just see if it qualitatively, to you as a human, how's it looking? Is it making sense? Is it directionally right? A lot of in the end, the evaluations of these LLMs are down to human judgment. As you will have seen today, there's some new features in MLflow that help you do that. You can actually log a model to MLflow and automatically log some generations and actually vote on them in the UI. So there's some support for doing that. But plan to do something like that, if only periodically sampling a checkpoint. And you may want to just have a think about the time and cost up front. You may want to run like 1/100th of an epoch and see how long that took on your hardware and decide whether this is going to take 2 months and cost $10,000. Does that make any sense? Is that within your budget before you go too far? So preparing the data is probably the easy part. For example, in this case, because we already had question and answer data with context from Stack Overflow, well, that fit really neatly into the setup for the Dolly training script, which expects an instruction with optional context and a response. We have to all have questions, like in the title in Stack Overflow, Stack Exchange, plus the body, which is more context about the question, really, and then the answer, maybe the top voted answer to it. So we have in fact, any strings will work. At some level, these text generation models don't have a notion of questions and answers. They just are continuing strings that you provide. But if I just gave it sentences from my corpus, I would be training it to maybe not continue responses in the way I want. So if I'm just If the model just learns to continue prose, then if I ask a question, it might learn to just kind of continue my question. So that was the whole point of things like Dolly. We wanted to fine tune on examples of question and response or instruction and response to induce the model to continue a question with an answer, not with another question. This part's kind of art more than science at this stage. But in this case, I think it's pretty clear, and I can just assemble this data set really easily with Spark and a bit of Pandas code. It's really nothing. How much data to tune on? This is a common question. The key question I don't think is like how many bytes of data you have, but how many tokens? How many words, but really how many subwords do I have? And it's not so much how much data do you have, but how many times are you going to pass over that data? So we often, when we talk about a model seeing a certain number of tokens, that's kind of like the number of tokens in the training set times the number of times it ran over the data set. That's a more relevant way of thinking about the size of the training. I think it's worth thinking about the scale of the training of the model you're about to fine tune versus what you intend to fine tune on. For example, Dolly was created from Pythia, 12 billion. That saw 300 billion tokens during its training. That was just one pass over the pile. It's a big internet data set. Excuse me. And then we fine-tuned that for a couple epochs on about 30 million tokens. So it's, Dolly 12B saw 30 million tokens to induce its behavior. And in this example, I only have about 1.5 million tokens worth of data in this data set. So in a way, that's already a yellow flag, I think. We just don't have a lot of data for a very, very, very large model. And you can imagine what that might induce. Well, number one, I suppose if I don't train any model enough, I get underfitting. I don't really move the model much. But that's typically not the problem. The problem is typically training too much with too little data, and that will cause overfitting. And in fact, I think, as you'll see, unless you have a whole lot of data, you are going to memorize your data very quickly. You're going to overfit if you try to fine-tune, unless you're careful. And this is probably the biggest failure mode you'll encounter with trying to fine-tune. I suppose if you do have a lot of data and you train a long time, you get a third problem, which is forgetting. The model tends to forget everything it knew outside your data set, which might be a good thing. Maybe that's your intent. You kind of want the model to only know what was in your data set and not anything outside. But it's number two that I think is going to be the real pitfall. OK, so fine-tuning. Again, I'm not going to get into the details of all the tooling, but I would recommend using the high-level APIs like Hugging Face Trainer, using someone's existing training code if they've already written it, like in the case of Dolly. And one tool you'll find coming up over and over is DeepSpeed from Microsoft. DeepSpeed is, well, it's an accelerator for running LLM training. One major thing it does is help you trade off memory for speed. So it helps you make the training use less memory at the cost of some speed. It can also help you distribute over a bunch of GPUs efficiently as well. So if you're going to fine-tune, yeah, maybe start with a smaller model. Start with a short training script. If you can get A100s, yes, those are better for training for sure. A10s will work. And again, memory is going to be the bottleneck. So you're going to find yourself fighting with the settings to not run out of memory here. Tips, work in 16-bit here as well. The bfloat 16 if you're on Ampere GPUs for sure. Don't know that you need to go down to 8-bit. That's more problematic for training. As in all other deep learning processes, turn down the batch size. But with DeepSpeed, you get some more levers to pull. Things like gradient checkpointing, which really means don't keep all of the gradients in memory at once when you don't necessarily need them all in memory at once. You can recompute them. So there's less memory, but I got to recompute some stuff. DeepSpeed also helps you offload the optimizer and even parameter state from GPU memory to OS memory and even to disk. So it's got a lot of tricks up its sleeve for reducing GPU memory requirements. And ultimately, you can probably get DeepSpeed to train just about anything if you make this trade-off big enough, although it will go slower and slower the more you're offloading, right? No, there's not time to talk about LoRa and PEF, but there's definitely other things you can do to fine-tune that aren't literally fine-tuning every weight in the model. Like LoRa, that's training like a smaller adapter layer inside every encoder and decoder block in the model, and basically freezing the model and just adapting it. that is definitely more resource efficient. It requires less memory, fewer GPUs to achieve something like fine-tuning. So definitely worth looking at if you need to fine-tune. The only downside, by the way, it doesn't make the model smaller. You end up with an actually slightly larger model. So it doesn't make inference any easier. It makes training cheaper. But yeah, LoRa is an interesting one. It's also, by nature, kind of introduces some regularization, so it can fight that overfitting effect I mentioned. So worth looking at, but that's another talk. So if we've done all that, OK, well, yeah. If we fine-tune the data into the model, well, we can just use it to generate answers to our question, right? Same idea. I can still pull these levers. Now, I don't have to feed any context from a vector database in. So I just sampled some outputs from the result of fine-tuning this data set into Dolly, actually. And I'm not sure it's better. Now, maybe I did it wrong. I think this was problematic, which I'll say a little more about. But as you look through it, yeah, it did OK. I mean, certainly turning up temperature made it go really crazy. And when I induced more conservative responses, I still got some weird stuff, like a URL at the end. And I'm not finding that nice reference I know is in there that actually gives you a formula for the best blueberry soil. I didn't get that here. So in a way, I don't think this worked as well. In a way, part of my analysis is it is actually useful to find relevant, if you can find information relevant to the question and put it front and center by putting it into the model's context, in its context window, that's probably a win because the model's going to pay a lot more attention to that. You've started it out by generating that context, right? Whereas here, it's just kind of, who knows whether that information is going to surface from those 12 billion parameters. But the main problem here, I think, is overfitting. And I tried this a couple times, and no matter what I did, I couldn't get away from this. This is the training loss curve from TensorBoard. The eval loss curve looked like this. It just kind of went up almost from the start. Training loss going down. That is classic overfitting, but the weird thing is the stair-step pattern. And if you think about it for a second, I think it's pretty clear what's happening. It's not getting better at answering questions, and even with respect to the training set. But every time it starts over, and it starts over right here in the middle, in another epoch, well, it gets a lot better all of a sudden, because suddenly it's seeing questions it's seen before in the training set. So it's clearly memorization's kicked in here, and it's really hard, I found, to fight this effect. I think it's due to just data size being too small here. So there's other ways you could approach this. With more data, this might work. If you're smarter and you know how to run this better than I did, you may be able to make this work. But I found in most cases, when I tried to fine-tune an LLM to get it to know different things, I ran into the same restriction unless I had a ton of data. And a lot of times people are looking at a use case like this. They don't have a ton of data. In this case, I had tens of thousands of questions and answers. You may have thousands in your private knowledge repo. You're going to run straight into this. So maybe that don't fine-tune version was better. OK, closing up. Next steps. If you liked this, hope you did. Number one, that demo link, there it is again. That's a demo of the don't fine-tune pattern. We also have an accelerator that's also a demo of the don't fine-tune it pattern. And it shows you actually how we built the agents, not the one announced this morning, but the one on our knowledge base site. If you want something more deployable, that second link is maybe an interesting example. There's the repo for the fine-tuning code if you want it for Dolly. That's what I was using. And by the way, we had some interesting new features announced today. GPU-enabled model serving, if you want to serve the results off the shelf or not. That's actually been around for a while in private preview. And coming soon, of course, vector search, vector index. Keep those in mind. If you like this, those are going to be very relevant product features for this type of work. So recap, sometimes you're going to want to customize an LLM's behavior. You want it to answer over your data. And hey, try off-the-shelf models first. Try open source models. You're going to use things like transformers, LangChain. For question answering, you may well use a vector database for context retrieval. And you're, in all cases, going to need to explore and test generation settings. They're probably not going to be optimal out of the box. Fine-tuning, maybe. You don't have to fine-tune. But if you do, you need to pick your base model and data set carefully. You're going to need to spend some time getting training to run and not run out of memory. Get to know DeepSpeed. But if there's one thing I think you saw today that you've learned, and I'm sure you won't forget, it's how to grow blueberries. Yeah. try it. Great. Yeah, in closing, leave your thoughts about this session. Here, you can leave feedback. If you haven't got the app, open the app, find some more sessions. I think the day's kind of over, but there's a whole full day tomorrow. And consider training and certification at Databricks here at the summit as well. And I think that's it. Thank you very much.